Starting, all attendees are in listen-only mode.
Well, hello, everybody. Welcome to Coffee with Caleffi. I've got a really exciting presentation today, and I was very fortunate to score Kevin to help us with this from Dow. He's what I would call the guru of glycol. He's been with Dow, almost 30 years now, Kevin? Did you say, you're just a week short of 30 years or something?
That's right, Bob.
You get a gold watch or something for that? Or
I haven't picked it out yet, but I'll get something.
All right. Well, thanks, and thanks for joining in today. Sorry, I misspelled his name, too, by the way. It's with an O-R at the end, but it's right at the end where we've got his contact information and stuff. But we're going to kind of tag team on this a little bit. We've got some of the slides from Dow. Kevin was able to bring some of his slides along. I got some that I built, so we're going to kind of jump back and forth. And Woody's going to monitor questions, and I think what we'd like to do, if we can, is I didn't put a lot of slides in this one. Sometimes I overload a little bit, and then I rush towards the end. So I tried to keep this one a little lean. And hopefully if there's a question, we can get to it while we're on that slide, because sometimes we'll get to the very end of it, and the questions come in, and we don't know which question refers to which slide or something like that. So Woody's going to kind of interrupt if there's something that's really important that pertains to a slide, because it benefits all of us if we can get the question answered when there's everybody online. And by the way, this is one of our largest ever by a long shot. We had close to 600 people signed up for this today. So this must be a topic that's of interest. And, it seems every time I go out west, I've been in California and Colorado, Montana, Idaho recently, a lot more glycol gets used out there because of the, the climate up there. A lot of homes up in the mountains and stuff like that. So this is a huge product, a huge market in our industry, both for the cooling and the heating side of it. So we're going to get started. Again, you can type in the questions as we go along. And just quickly, a couple housekeeping things. Hydronics, we've covered a lot of different topics. Number 17 should be out probably within the next couple weeks here. We're going to do one on buffer tanks for number 17, and then I think on 18 we're talking about doing something on system fluids, which again would cover glycol as well as water and the importance of using good quality water in the system. So if you're not on our mailing list for the Caleffi Hydronics, just go to our website and sign up, and we'll get you on there and mail them out to you twice a year. Something you might be interested in too, Kevin. There's some good information in there that might pertain to what you do.
Yeah, sounds good.
So I'm not going to read through this list, but quickly everybody go over that. And if there's a question on there that we haven't gotten that's been on your mind, certainly we'll answer that. But these are the ones as we, as Cody takes questions on our tech support line up in Milwaukee. These are some of the most common questions that seem to come up over and over again. And as I talk to installers on job sites and even the wholesalers that sell the product, with the various suppliers across the country, these are some of the questions that I think are the best addressed. So we're going to get to those and whatever else you have. So the wheres and whys of glycol. So I think I'll ask Kevin, this is one of his slides to take over. I know that there's different products that are available there. There's different levels of the products. There's EG, there's PG. Why would I use one over the other? So go ahead, Kevin. Tell us what you know.
Yeah, so for glycols, there's two families, ethylene and propylene glycol, that are out there. And these glycols get used in a variety of applications. The important thing to understand is ethylene glycol is moderately toxic, so that means a half a cup will kill the average size adult. Propylene glycol is approved as a direct food additive, so it's non-toxic. So really, and you make the choice. If you want a safe option, then you're going to go with propylene glycol-based product. If you're worried more about cost and performance, then ethylene glycol is the product you would use. And of course, there's other things out there. People ask the question, well, why is glycol out there? Why not something else? It really comes down to the other options really aren't that good. And alcohol can be used, but you have to worry about flash point and fire risk. There's salts out there, but they're terribly corrosive. And in anything that doesn't have water, it really suffers from a heat transfer perspective. So really, at the end of the day, if you want to freeze protect water, then a glycol-based heat transfer fluid is a really nice option for you. And we've got some pictures there of the Dow fluids that we sell. But there's other fluids out there. And by and large, it's either ethylene or propylene glycol.
But now ethylene is still viable. I know in bigger jobs like commercial jobs, sometimes university and stuff. I mean, that's still viable if it's not in contact with domestic water or something. Is that the biggest option?
Absolutely. And think refrigeration, like ice skating rinks and the like, will tend to go with ethylene glycol-based products because at the low temperature, the viscosity propylene glycol is quite a bit higher than ethylene, and that affects your heat transfer and affects your pumping horsepower. So absolutely, ethylene glycol is still a viable option out there. It really comes down to making that choice, performance versus safety or environmental impact.
And that's a good point for skating rings. We never think of that way. I mean, I think in our industry we always think of it as a heat transfer fluid in a pipe, but it's certainly used for a lot of other. I mean, in the food processing industry, I mean, it's used in the toothpaste and a lot of different things. Now that's a question I always had. Does all glycol start out as a food base, and then as the additives get added into it, it becomes a different fluid, or do you start with a different grade when you go into like a technical glycol for, hydronic applications and stuff like that, or does it always start as the same?
No, it's a great question. So first of all, there's no such thing as food grade ethylene glycol, all right? So, but on the propylene side, not all grades of propylene glycol are food grade. There are industrial grades or technical grades that don't meet the specifications that FDA establishes under the Food Chemical Codex. So if a product says that it is made with food-grade propylene glycol, well, that necessarily means or implies that it meets those Food Chemical Codex specifications. Industrial-grade PG won't meet those specs, right? So it won't have the same low toxicity as the food-grade PG. It really depends on what else is in there from a contaminant point of view. But it's an excellent question in the sense that nobody goes out there and kind of advertises what they really have. A lot of people make the assumption that glycol is glycol and all propylene glycol is the same. Well, it's not. You need to be careful, and if you want a food safe type product, then make sure you get that. Don't get hoodwinked in buying a product that doesn't meet your needs.
Yeah.
Okay, I got a question here.
Okay.
It's appropriate. Okay. Let's see. Are there material limitations to using EG? Certain plastic piping products, for instance?
So in general, ethylene glycol will be a little more forgiving than propylene glycol from a materials compatibility perspective, okay? But are there limitations? Yes. And in things like PVC and CPVC, you need to go check your pipe manufacturer for their recommendation, because some say don't use our products, our PVC, CPVC, with any glycol at all. Others will say, well, you can use them, but don't exceed certain concentrations, whether it's 25% or 30% or whatever. And then others will say, we don't have any issues at all. And I can tell you that PVC is widely used, and so there's no reason chemically why you can't have, compatible pipe. But I guarantee you that there are issues out there, and because of that, some pipe manufacturers don't recommend using their product with glycol. And that really is a great question, because that is something that you all need to do, is to verify whatever material you have is compatible with the glycol. And so you go back and ask them, well, what's your temperature rating for your product with ethylene or propylene glycol, whatever you're using? Very, very important that you kind of get that sorted out before you build your system.
Okay. At the percentage you're going to use too, because I know when we first started doing fire sprinkler work, the PVC pipe we're using for that said absolutely not. We had to go to glycerin, which was a really ugly product. It's never been done that road.
You're exactly right, Bob. That was a recent change that NFPA made, where they no glycols allowed in CPVC, PVC, fire water sprinkler systems. Absolutely. Yeah.
Okay, I got another one before we move. If high temperature, high pressure designs are used, at what temperature does the glycol break down?
Well, see, and this is a very common question you get. And at the end of the day, any organic liquid degrades at any temperature. The issue is the higher the temperature, the faster that rate of degradation occurs. Okay, so we'll publish recommended temperature limits, and for the case of our fluids, about 250 Fahrenheit represents the maximum operating temperature, okay? And what that means is, well, let me back up. What it doesn't mean is everything is wonderful up to 250 and all hell breaks loose at 251. It doesn't work that way. It means from going from room temperature all the way up, you get a gradual increase, well, not so gradual, actually exponential increase with temperature. And then once you cross the line at 250, you start to get into the territory where you won't get useful life out of your fluid. The temperature's too hot, the degradation rate is too high for you to get a meaningful or practical life out of the fluid. And practical life in our business, we'd like to see at least 5 years as a minimum for a fluid to last.
Okay.
And then HDs will go a little higher than that. But we're going to get to that temperature thing. We got some charts on that coming up. So some of these questions I think will get answered too. But and now pressure doesn't have anything to do with it, does it, Kevin? I mean,
not really. Well, pressure is important in the sense that you have to maintain adequate pressure on your system to prevent boiling. Okay, so adding the glycol will increase the boil point, but it's not terribly different from water. Right. So if the fluid itself boils at say 220F and you're running at 250, you have to have pressure on that system or it's going to boil. And when you boil a fluid, it's not designed for that. The additives tend to come out and you get loss of additives, you get scaling and issues. So in the sense that pressure, I mean, it is critical to keep the fluid from boiling. So you need to pressurize the system about 5 pounds per square inch above the expected vapor pressure of the fluid. And we publish vapor pressure of our fluids.
And I know we're getting to that. We've got charts and stuff that in your engineering guide that show those all those points, which we're going to get to too. So before we get too sidetracked here, but I mean, the bottom line for us in our industry is typically freeze protection is what guys are buying it for, but it does bring a lot of other good things along with it, you know, in addition to the freeze protection, and that's corrosion protection. I mean, if you're putting a system in with all brand new copper pipe or steel pipe or cast iron boilers, whatever it may be, there's inhibitors, there's products in the inhibitors, I guess I would say, that would passivate that metal, that protect that metal from getting additional corrosion, buffers the pH. You know, the trade-off is going to be a little bit of a performance hit as far as pumping power and stuff required. But if you look at, you know, all the pluses, I think some of that sometimes gets overlooked. And they say, well, we're just putting in there to keep it from freezing with somebody. And we talked a little bit about the alcohols. I know Kevin did. But the other thing that I learned recently from one of the pump manufacturers, they said there's nowhere in any one of the pumps that we manufacture that has ever been approved to pump a flammable liquid, which is what the methanols and ethanols that are sometimes used in geosystems are. So just putting the pump into that application, you're kind of, I don't know if I would say voiding the warranty, but you're using it for an application that's never been tested or approved for. So just keep that in mind too. So yeah, I think we'll get to that pressure thing, because when we talk about solar, that's one of the big things is you know, potential to stagnate a collector, which means there's no fluid flowing through it. The pump goes out, the control goes out, or something like that. So by having that pressure on that system, we raise the boiling point of the fluid. And down most of the other products you're going to see out there have a heavy-duty or solar-specific fluid that has a little bit higher operating temperature. Again, I don't know what do you do differently to the fluid when you call it an HD and say it's good to 325 instead of 250?
Yeah, it really comes down to the additive package that you use. So in our case, our regular Dalfrost is made entirely from food-grade components. So you've got that USP food-grade propylene glycol plus food-grade additives. The HD contains some non-food grade additives, not at a high enough level to affect the toxicity, but at a high enough level to impart higher thermal stability on it. So that's really what it comes down to, Bob. You have to have the right additive package when you decide to freeze protect with glycols, because what works for water isn't going to work for glycols. It's totally different chemistry. You need to be careful. And I think we're going to get into more about that in a future slide. But really, once you decide I need to freeze protect, then you need to understand what that means with respect to how glycols change your ability to operate.
Yeah, and so one of the first ones I want to talk about is the freeze protection, since that does seem to be the major motivation for people to go out and consider buying a glycol to put in their geo or hydronic systems, whatever it might be. There's a couple different numbers to be aware of there. the freeze protection, burst protection, and some of them even list 3 different temperatures. The freeze protection where, an ice crystal will start to form, but you can still pump it. Then there's a slush point that, from what I understand, it becomes like a snow cone, that it's not going to burst the pipe, but the pumps, a centrifugal type of pump, can no longer move the fluid through the system. So you're not going to be able to move heat to the building or chilled water, whatever it might be, once you get to that point. And then, of course, the burst point where it's going to freeze to the point where it expands. And anything that I'm missing there is that I know you have tables for all that, and I think on your table that I show in the slide there for the Dow-Therm, by the way, then that's the EG, right?
Yeah, and so really it comes down to freeze protection. Like you said, that's the temperature at which ice crystals first start to come out of solution. And at the end of the day, a little bit of ice isn't going to cause damage with respect to rupture of your piping. But as you go colder below that freeze point and you get more and more ice crystals form, ice has got a lower density than liquid water, and so you get that expansion. And that's what that creates the pressure that causes rupturing. Burst protection means you've got enough glycol in there that it prevents too much ice from forming, and it prevents the ice from kind of agglomerating and forming bridging, I guess, across tubing that can cause rupture that way. So at the end of the day, freeze protection is the safer way, because if you've got a freeze point that's lower than the coldest anticipated temperature, you will have no chance of rupturing your equipment because ice will never form. Burst protection, you can get away with a little less glycol, but you got to make sure your fluid is capable of flowing to relieve that pressure as ice crystals form. And we kind of talk about that in our literature some more. But
okay, here's a question. Are these freeze, slush, and burst points for idle fluids?
Well, it doesn't really matter. Yes, so the freeze point is irrespective of whether the fluid is moving or recirculating. The burst point is a function of not just the fluid, but also the equipment design. So if it's a stagnant fluid and it's in a coil and it's a very narrow gauge or tight spiral, thin gauge material, that's going to have a rupture strength that's not quite the same as heavy gauge, straight length steel pipe, say. And so the burst protection is a little bit, we publish data, but at the end of the day, it's probably conservative in the sense that your equipment may be able to handle lower temperatures than what we publish. But then again, depending on what you have, it may be the other way. So it's dependent on equipment, and as well as the freeze point of the fluid, if that makes sense to you.
Yeah, and that's a good point, because a lot of the heat exchangers on things are getting thinner and thinner walled copper. If you have Schedule 40 steel pipe, and you've got a lot more fudge room in that type of pipe than you do some of this paper thin copper that I'm seeing some of these air coil heat exchangers and stuff. Now, gosh, it's like it's like tinfoil gauge metal that they're using anymore. It takes some cost out and stuff like that. So that would be more of a consideration to make sure you got that low number to protect that, right?
Yeah, exactly.
All right, and then the other biggest mistake that I've seen from what I've learned in the industry is having a clean system when you put it in there. Because even brand new pipe that you get off the shelf is going to have potentially thread cutting oils or something from assembly, if it's iron pipe or flux in there, or when they extrude the pipe, or if they assemble a boiler and they're using lubricants or different oils and stuff like that. So even a brand new system really should have a cleaner put through it first before you put because you can ruin the glycol the very first day you put it in if you haven't cleaned the system properly. So there are some numbers that have been put out there for what the water should look like that you use to blend it with, but clean it first, and then if you are going to blend it on the job, if you're going to buy full strength glycol, that these are the numbers that I see published everywhere as far as what, but the question then becomes, how does the average contractor know this? How does he know that, you can test hardness pretty easily, but as far as the chlorides and sulfates, how would a contractor on the job know that his water is meeting the spec? At some point, it's usually either buy the pre-blended or make sure that you've got a device or that you're buying deionized water if you're going to blend it on the job. Anything, am I missing there?
Yeah, I think, quite frankly, you should assume it doesn't meet these specs if it's potable water or wherever your source of water is. Unless you're purchasing purified water, whether it's distilled, deionized, RO, the odds are what's coming out of the tap isn't going to meet these specs. And so it comes down to the old adage, do it right the first time. Because if you don't meet these requirements, you're going to pay a price later on in life. And really, that's what it comes down to is, you know, people like us, we learn from our customers' mistakes. And so then we publish recommendations to try and help the next one, and on it goes. And so, you know, follow the recommendations. They're not made lightly. They're based on real-world experiences, and you'd be better served to try and do as much as you can to do it right the first time.
Well, and that's excellent advice, because as I look at that list, the only number that I, know how to test or could find out on the job would be the hardness. I got a little hardness test kit there, but I have no idea how I would test for sulfates or chlorides or, some guys have TDS meters that can read the conductivity, but that's a good point. Just assume that it's one of those is probably, if not all of them, are going to be out of whack. That it's going to.
Yeah, the conductivity for the water itself is a good proxy for quality, right? I mean, pure water has no conductivity. Mm-hmm. So if you can do that's not a bad test. Don't go with conductivity when you've mixed it with a formulated glycol, because that conductivity will be off the charts because of all the additives that are in the glycol. But the water itself that you use to dilute should have very low electrical conductivity.
And we did have another fellow, a geo expert, that came and did a webinar a couple of years ago for us, and he uses his ohm meter, his regular electric ohm meter, and takes a little glass of water, and you can stick it in there and see what the resistance. I mean, you could turn that into a TDS number, I guess, if you had a multiplier or something for that. But, I mean, that's really what it is. If there's minerals or anything in the water, it's going to read across those two probes when you stick your ohm meter.
Yep. No, that's exactly what they do in a lab. When you deionize water, that's how you verify that your ion exchange resins are still functioning and they don't need to be replaced. So.
Doing their job, yeah. The other caution, of course, when you do put it in the hydronic system is make sure that you've got the pumping power. And again, when we get to the end, you've got tables in the back of the engineering guide from Dow that show you how to do this calculation, or here's a formula if you're a number cruncher type of guy. But just an example that we put out there, let's say you've got a customer that wants you to come over and put antifreeze in the system. They're going to Florida for the winter. And you go over there, and this is a fairly typical system, 50,000 BTU, little boiler and some 3/4 copper pipe. We've got a pump in there that's going to circulate that just fine with 48 watts, but then we put a 50% mix of propylene glycol in there, and it makes a huge difference in the amount of pump that you need to move that. I mean, huge in relation to, 48 to 68 watts, something like that. You might be able to get away with the pump that's already in there. If it's a multi-speed pump, you might be able to bump the speed up, but there comes a point when you might have to increase the pump side to make sure you can move that amount of heat to it. Now, that's not going to, again, cause it to freeze or something like that. It just means at some point that if the pump was undersized, you're not going to be able to move those many BTUs through the piping. So just know that there is a multiplier and tables available to come up with that correction.
Yeah, and it underscores the point made earlier that, you're adding glycol for freeze protection. If you don't need freeze protection, you would take an unnecessary hit in your system capacity and your pumping horsepower by adding the glycol.
Yeah, and we'll get to more slides on that as far as the heat transfer, too. So you take a hit on the heat transfer as well as the pumpability, if that's even a word, of the fluid, right?
That's correct.
And this is where it's gotten really complicated in our industry is more and more we're seeing, back in the day when I started in the plumbing business, we had cast iron boilers and copper tube, and that was pretty much it, some steel in there with the expansion tank, and we had 3 metals in there. It was a fairly simple system, but now, as the efficiency of equipment goes up and manufacturers look for other materials to make equipment out to save cost or make them last longer, now we've got stainless, we've got aluminums with a lot of different alloys in them, we've got composites that are starting to show up in the picture now. So I know that presents a challenge for the people that blend these fluids to come up with a fluid that can cover a wide range, because what works for copper and cast iron, might need to be blended differently for aluminums, for example. I know most of the products now have an AL label or something like that saying that they are suitable for aluminum or aluminum alloys, I guess I would say, in this system.
Yeah, it's a good point. Not all fluids are, it's difficult. No, let's back up. It's impossible to have a fluid that is, provides 100% protection to all different kinds of metals. You really have to be, when you're designing a system, fewer is a lot better than better option than when you have multiple metals. When you start doing aluminum with stainless and carbon steel and copper, it's almost impossible. It really is, to protect all those metals from corroding. Something's got to give. And so you're better served to minimize the number of different metals that you have in your system when at all possible. But to Bob's point about if you've got aluminum and your temperature is elevated, you want to make sure you pick a fluid that's designed to protect aluminum, because that's typically going to be your weaker link. So read the label and choose the product that meets your needs.
Yeah, and I think the number is something like 150 degrees in aluminum, right, is where it becomes
for our fluids, that's what we recommend. If you're not going above 150, you're fine. It's not going to be a problem. When you get over that 150, you can have problems. And Dow being very risk averse, we don't want any problems. So we say don't go above 150 with our fluids. Now, we have other fluids in Europe that are compatible with aluminum. And if industry trends continue, we may be bringing those products here in North America. Right now, I struggle with why aluminum is, the increased usage in a home heating. I get it in a transportation vehicle where you're trying to lightweight the vehicle, but there are better materials from a longevity perspective than aluminum, and it's one of those things that we'll see. If we need to bring our European products over here, that's fine.
Well, and aluminum's not a great heat transfer metal either compared to copper and some of the other things out there, so you're taking a hit there too. But from what I understand, sometimes when you bring other products in, now you got to make sure they meet all the other requirements as far as being safe and other things. So something that's blended highly, or you put more chemicals inhibitors in, it might not meet the FDA and all the other requirements for low toxicity and stuff, right?
That's good. Excellent point. That is very true. If you need to have a product that's entirely food-grade materials, that really ties your hands in terms of what corrosion protection what metals you can fully protect from corrosion. So at the end of the day, though, get a product that's designed for the materials that you're using, and you can see the pictures on here. What happens when you don't? If you just have plain water, or you just put plain glycol in that plain water, you're going to be guaranteed to have a corrosion problem. And those examples are for carbon steel, but other metals, I could show pictures of other metals. And then you see the one with our Dalfrost HD carbon steel looks brand new, and that's 5 years as it explains in that slide. So it is possible to have formulated products that are going to provide you with the corrosion protection that you need. You just need to make sure you get the product that meets your system needs.
One of the challenges that we came across is, when some of these high-temperature solar collectors started hitting the market, these evacuated tube collectors, the stagnation temperatures on those is well over 400 degrees. I mean, it can go up to 500 degrees. So finding the fluid that could, we don't want to see them go into that condition, but knowing that it's inevitable at some point that system's going to go into stagnation, that what kind of fluid to use in that. And from what I heard, and I don't have proof of this, that some of the chemicals, that some of the glycols that were coming across from Europe to go into those systems to make sure they had the protection might not have, made that EPA rating, or might not have had that approval on them. So, like I say, you can get a fluid that'll do it, but you certainly don't want to risk that getting in with the potable water somewhere. So I hope it doesn't drive us back into dual heat exchangers to be able to handle these high-tech fluids if that's where we get pushed because of the, for example, aluminum or something like that. We get a chemical that now we got to really protect it from the domestic water. So this is a friend of mine, a contractor out in, I don't know if he's tuned in today. I see my son Max is on there. Hi, Max. And this I thought is interesting, that the job he goes on, he takes a sample of the fluid and then takes it back to the shop, and you can test it there for different things. And you can see on the right there, those are all different, fluids that he's taken out of systems up in Colorado. And you can see the condition of the fluid. Some of them look like it's brand new, like you see on the upper left there. The fluid's good and bright and clear, like it, or colorful like it went in. And some of them are getting darker. Some of them have sludge in the bottom of them. Some of them obviously didn't have any protection in there, just clear water in them. But so you can see it's happening out in real life. There's quite a range of what's going on with these fluids. So, I mean, typically in a boiler system, Kevin, what would cause a glycol to go bad where it's not seeing, solar 300-degree temperatures. Let's say the boiler never operates above 180 degrees. We're seeing fluid that's going brown or bad like that. Is that from oxygen getting into it typically, or what caused the fluid to fail?
It's oxygen, heat, and failure to maintain the pH and the corrosion inhibitors in their acceptable ranges. The discoloration can be caused by thermal oxidative degradation and corrosion. And so really, it's a great slide because a visual inspection of your fluid, you may not be able to know exactly what's wrong with your fluid, but if it looks funny, it looks bad, the odds are there definitely is one or more fluid parameters that are out of range. And so it's a simple but powerful test you can do for your fluid. And if you put it in at water white and it's starting to look amber, well, you're probably okay, but you've done something to it. And then as it goes from amber to brown to black, well, you want to get it out of there before you have a real system problem.
Yeah, and just, a bottle of water, take a bottle of water with you, drink the water on the job site, and then put some in there. It's probably the very first best step you could do is just take it out and look at it, smell it. It has a funky smell when it starts to go bad like that. That dark colored stuff, it certainly smells a lot different than the new stuff out of the bottle. But in some cases, it can be saved with an inhibitor. I think we'll get to that a little bit later. In some cases, it's time to just flush it out, clean it real good, and start over because it can't not affordably be salvaged, right?
Yeah, no, that's very true.
This one here I put in, this was a slide that we used for some other thing, but it just really shows any kind of buildup inside a pipe or a heat exchanger, whether it's a boiler or even a heat emitter, a panel radiator, a radiant tube, or anything that has to transfer, the heat through the fluid in it. If you get a buildup on the wall of that tubing or the wall of that heat exchanger, it doesn't take much of a buildup before you start hampering your heat transfer ability. So if you've got a boiler with a big burner in it and you're trying to get the heat from the burner into the fluid that's in there, and you've got a coating of glycol that's caked in there because it's been burned because you didn't have flow rate or something through it, you're going to take a hit not only the glycol going bad and causing problems, but also the heat transfer when it's in there trying to do its job. So it's kind of a double whammy there when things start to go bad with fluids if they start coating out. We talked about this already, I think, a little bit earlier. Maybe you want to talk about it some more. But I did learn something doing the research on this, that geofluids are typically at a lower percentage because we don't have the extreme temperature range that we might have in a house or something. But I think we talked about that. More pumping power might be required, depending, of course, on the fluid percentage, too. I mean, my suggestion always don't mix it any richer than it really needs to be to do its job. Just because it comes out of the bucket as a 50-50 mix, you might not need it that strong, and so that could be ordered differently or blended with some deionized water to get it down where it's a little bit more pump friendly and a little bit better heat transfer.
Yeah, but I think you have to be careful. I wouldn't agree with this 23 degree. I think that's a little too weak a concentration. And one of the problems that you have with glycols at the weak concentration is they're very biodegradable. And you get too weak, you're going to have your fluid biodegrading in your system, which is not a good thing. As you get up in concentration, 20 to 25% or more, so you're going to be in the 18F or lower freeze point, then there's too much glycol in there. It basically imparts osmotic pressure, which dehydrates cell tissue. So bioorganisms can't sustain themselves at concentrated glycol. Greater than 20 to 25%, depending on the product. But you go below that, and that osmotic pressure is not high enough, it's bug food. It's going to feed off that glycol, and you talk about odors. You'll get some really funky odors when you start having a fouling problem.
So bacteria really is growing.
Bacteria, absolutely. There's airborne, waterborne bacteria you inadvertently get into your system. If you don't introduce any bacteria or fungi, you're fine. But if you do, you've got bug food if you go too weak of a concentration. So be careful.
Yeah, well, that's a good point because I never thought the low end. We're always worried about the high end, but good advice there. Thanks. Yeah, test. I got that's the key to maintaining it and catching it before it goes too bad, like some of that we showed in a couple slides back there. This is what I use. I think this is what you recommend in your operating guidelines in your technical brochures. There's a little refractometer for testing the freeze protection. So the one on the left here, that's basically what that's doing. Is you just open this little window, you put a drop of it on. There's actually a little dropper on the side of this tool, and then you close the window, and actually when you push it down, a light comes on in there, so you can read the scale really good. But I mean, for the cost of that tool, I don't know why you wouldn't own that. I think it's just a little bit more accurate than the floating ball type of thing, and it's certainly a durable product. So that's the one. And then the other important tool here is the pH meter, because isn't that going to be the best barometer for the average guy to check the pH? That's going to tell you if you go back every year and it's dropping, that number one, something's going wrong, and number two, it's going to get to a point where you're going to have to either boost it up or replace it.
Well, definitely low pH is a clear-cut indicator you have a problem. But pH within that range, 8.5, 10.5, may or may not be telling you the whole picture. So when metals corrode, they tend to release free hydroxide, which keeps the pH up in the alkaline range. So you can be fooled by pH, but clearly if it's acid, you have a problem. If it's in that range, you still may have a problem. And that's why I go back to the visual inspection, because if it still looks water white or clear, and you're in the pH is good, that's a real good sign that everything is copacetic with your fluid. But yeah, the refractometer is a good way to check verify you got the freeze point, the glycol concentration that you desire. So that's a great tool, simple tool to test.
And it does read, this one I think reads EG and PG when you look in the scale.
They usually will have a dual screen or dual scale on the viewfinder, and you look on one side for the ethylene and the other side for the propylene. So you need to know what fluid you put in there. It can't tell the difference, but it can tell you what the freeze point will be for either fluid.
I like this line that you got at the very top here that, go back a week or two later and check it then, and that gives you your baseline. So then every year when you go back, or every couple of years when you go on a service call for something, check it again. Because if it's moving, that's the indicator more than, where it is, but the fact that it keeps moving down.
That's an excellent point. Yeah, get that baseline, make sure you did everything right. And if you do it right the first time, you will reap the rewards, because you will have a long-performing and an adequately performing system. If you do it wrong, you're going to pay a price. It's just a matter of when.
Yeah. And now, does pH ever go up, or does it always go down as glycol?
No, it can. Like I said, it will go up, and that usually is a telltale sign you've got a corrosion problem. So if you're using aluminum and the pH goes up over 10.5, guaranteed you have a problem with your aluminum heat exchanger.
So the aluminum is breaking down and it's affecting the fluid pH.
Yes, it's forming aluminum hydroxide, right? And that hydroxide pushes up the pH. So, be very careful about pH that's outside that range, because that definitely is an indication you're having a problem if it's outside that range. But don't be lulled into sleep thinking, I'm within that range and I don't have any problems. Look at your fluid, because it'll tell you.
And then what would a contractor do? So he looks at it, it's within this range somewhere, but it's getting dark. It's brown, or it's a coffee colored. What do you do? You'd send
Well, if it's a small system, I wouldn't mess around with it. I think I would just replace the fluid. If it's a large system, you're talking a school or hospital hot water heating loop, well, then that's when a company like Dow comes to mind, and we can analyze the fluid and do the test needed to know whether that fluid is still acceptable for continued use or not, or whether it needs to be adjusted and add more inhibitor or boost the pH back up. There's lots of things we can do.
But the important thing, I guess, for the contractor is to find out why it went bad. Was it because it was, mishandled when it was first put in, or is there something, somebody opening that system a lot and getting into it and allowing a lot of oxygen? Something's causing that to happen.
Sure.
The fluid just doesn't go bad for no reason.
No, that's right. And the fluid analysis will help you get to that, track down the reason why that fluid is bad. And and you can't tell everything from the fluid, but if you do a comprehensive fluid analysis and then combine with the knowledge that the contractor or the owner has for that system, you can normally sort with the two sources of information. You can normally track down what went wrong and how to fix it.
Yeah, and I mean, this is a classic example where you would find if that aluminum is, not to pick on of aluminum, but just since we started with that, I mean, it is a less noble metal. It is the probably weakest metal that's going to go first, but this type of test here would say, well, that's what's in your fluid, your aluminum, right?
Yeah, we can look at it, and in fact, we measure all of the metals. We'll check for aluminum, copper, zinc, steel, or iron, manganese, and chrome. We'll look for all the types of metals that can be there, and if they should, but ideally, if the fluid is within its recommended ranges, you won't see any of those. But if you see one or more of those metals, usually there will be some other parameters, whether it's pH or your inhibitor's been exhausted. There'll be a reason for why that metal content goes up. So it's just part of the service that we provide for larger systems. And so, I mean, it's something, if you're not taking advantage of that, you oughta, because it's a service that Dow provides to help customers maintain their fluids.
And I don't know how you came up with that number of 250, but I
just
found they can get a hold
picked it out of the air. I don't know. I mean,
but if somebody's having a problem even with a smaller system, I mean, they can contact you or their distributor, whoever they're getting it from, and certainly there's help out there, right? So here's an example of what the report would look like. And again, I don't know that we need to go through every one of those, but it's certainly got a lot more information on there than you could get at the job site.
No, that's right, and it's really interesting how all that information on one piece of paper like that, and yet it takes about $1 million worth of lab equipment to generate all those numbers. And so it isn't something you're going to have at the job site. You couldn't possibly afford all that. So again, it's something that we provide for larger systems. If it's a smaller system, it's going to cost you more to analyze the fluid than it does to replace it. So that's part of the reason why the 250 gallons or more of concentrate is put out there. And then on top of that, very, very difficult to adjust a small, like a 5-gallon or 10-gallon or 100-gallon, even 100-gallon system. Very difficult to adjust those in terms of adding inhibitor or pH booster.
So just start over. And at that, you probably want to put a cleaner in there and clean out the system.
Exactly.
All right. Any suggestions for cleaners or something like that?
Yeah, it's a good question. So I'm an advocate for keeping it simple. So I mean, if it's a brand new system, as you mentioned, it's good to flush. Use water and maybe a mild degreaser, something like as simple as trisodium phosphate. A 0.5% solution of TSP in water is a nice degreaser. That'll help flush. There's other products out there that you can use, and you consult your distributor to see what's available in your area. But by and large, keep it simple. The only time you need a really complicated descaler and varnish removal type products is if you've had a problem. You've overheated the system, or you've used very poor quality water, and a simple water TSP type flush isn't going to do anything there. In that case, you may end up replacing some of your equipment too. If it's it may be more cost effective than trying to use the necessary chemical cleaners to get all that stuff off your pipe walls and heat exchangers. So.
Yeah. Now this slide, this was a presentation that Jim Paling did a webinar for us here a while ago on fluid quality for steam boilers and boilers, and this was a part of a research he did, and he found this old DOE research paper. And one of the things that happens in our industry, Kevin, is there's a lot of, not a lot, but too many systems out there, might be a better way to say it, that have a tube that doesn't have an oxygen barrier. And as the water, the fluid's heated in there, the oxygen migrates through the wall of the tubing, the molecule, and it gets in there and obviously consumes the oxygen scavenger, whatever components in the glycol package that does that. And then the glycol gets depleted and things start going bad. And that, again, going back to Heatmeister's slide there, a lot of those bad burned glycols that you saw were, in fact, from old rubber tube or polybutylene systems that allow oxygen to get in there. So that's what this was showing here, how the, I don't know how well you can read that, it's pretty small print, but anything about oxygen ingress into a system? I mean, is that...
No, it's exactly right. Anything you can do to mitigate or prevent oxygen ingress is critical to the lifetime of your fluid. So really the the lifetime of your fluid is a function of temperature and the degree of exposure to air or oxygen. And if you've got high temperature and you've got high oxygen ingress, you're going to have short fluid lifetime. It's going to degrade very, very quickly. And this was an excellent series of papers that Rossiter published in the 1980s, and there's a number of them. And he goes through all the different metals, and it's interesting. You have the one with copper there. Copper is an incredibly powerful catalyst for any kind of water-soluble organic, whether it's a glycol or an alcohol or whatever. It facilitates that, catalyzes that oxidation even better than, say, carbon steel or other metals. So it's really interesting. They did a lot of good work, but at the end of the day, it comes down to temperature, availability of oxygen versus fluid lifetime and the type of metal. So those things can affect your fluid lifetime.
Yeah, and what we've learned too about the oxygen ingress with these, the PEX tubings or the polybutylene tubings that didn't have an oxygen barrier, is, like you said, the higher the temperature, the faster, the more O2 ingress there is. So if you're running a 180-degree baseboard system, for example, your fluid might, you could be talking a year, you could destroy a fluid like that if you've got a lot of that tubing and you run at those elevated temperatures. So,
absolutely true.
At that point, it's time to separate that system with a heat exchange or something. So, we've been talking around this. I guess we went to the slide, but this is everything we've been talking about: the impurities and the air ingress. Not air, but O2, right? Air, oxygen's in the air, but if it keeps getting there, because people say, well, how is air getting in my pipe if water isn't leaking out? Well, it's not air like you're thinking that we breathe. It's actually the molecule of oxygen that can get through the wall of the tubing or in around a pump seal or in around a packing or something like that. So. I think you've hit all these points pretty well here. That's, like you say, at some point, you can't buy enough inhibitors. The cost to put inhibitors in there and to try and salvage a bad fluid. I know, what do you say, somewhere in the 7 pH, it's time to start thinking about getting that out and starting over.
Yeah, and also as those degradation compounds continue to form over time and temperature, you reach a point where the concentration is so high, it doesn't matter how much additives you put in there. They can't compensate for the negative effects, right? These degradation products, they overwhelm the good that an additive package can provide. So that basically forces your hand, and you say, well, that's it. I've reached the point of no return. I've got to replace my fluid now. And that, just tying back to earlier slide where we talked about glycol quality, that's why it's so important to start off with a glycol that has a very high purity. Has very minimal amount of contaminants to begin with, because they're going to form with time. So if you don't start off with a high quality glycol, it means you're going to get to the end of the fluid's life a lot sooner. So.
And I appreciate, we weren't trying to turn this into a sales spiel for Dow, because I know you make the base product for probably a lot of different brands that these guys are buying, over the counter there. But, when you see a lower cost, there's a reason that some glycol is $6 a gallon and some is $12 a gallon. There can only be one answer to why there's a price difference, and that's probably a big discrepancy in price. But, it's like everything else. You really do get what you pay for in a fluid like that. And if it's, a customer with a pretty expensive system, that's really protecting that system for the life of the system. So it's really not a good place to try and to save a few bucks. At Caleffi, we're not really a player in this game. We don't really have a dog in the hunt as far as, we do sell a glycol fluid, but as far as equipment and stuff like that, I just wanted to show a couple things on the right there. We do have dirt separators and magnetic separators that if you do have a system that's, an old iron pipe system that you're going to have debris coming out of it, regardless whether there's water or fluid in there, we've got products to help keep that out of, harm's way out of the pumps and out of your system. So what else we got left here? I think we're down to the last couple. I think we talked about that. So we talked about the pump head, expansion tank has to increase a little bit because of the fluid. This is one here that is harder to get the air out of a glycol. And this hit home for me. I was at a trade show here a while ago, and they had a clear tubing display of an air elimination device. And I noticed the fluid was a green-colored fluid. And I said, oh, you got glycol or something there, don't you? He said, well, yeah, because we keep them in our trucks in the wintertime, and we don't want this clear display to freeze, so we put a little glycol in there. But he said, but you know what, we got to keep this non-foaming agent, because he said the demo doesn't work very good when we pump air in it to show the demo of how the air comes out with this piece of equipment they were selling. He said it can take like 15 or 20 minutes for that air to clear out of this little system because the glycol, what is it about it? I mean, am I pulling stuff out of my butt here? Does that make sense?
No, you're exactly right. The air release properties of glycols are very different than water, and it comes back to viscosity difference, right? So propylene glycol is going to be even slower air release than ethylene glycol, and of course water is ideal. Water, a very rapid air release compared to glycol. So it's just a function of the physical property of the glycol, namely the viscosity. And so you have to, in fact, when you're doing an installation, just remember it's going to take longer. If you've never used glycol before, it takes a lot more time to vent all that air out of the system. And so just don't be fooled thinking that, hey, I got it all out. And don't also be fooled thinking you got a foaming problem when really you might just have an air entrainment problem. You didn't remove all the air from the system. A foaming problem means those bubbles just don't collapse in a reasonable amount of time. So you've got coalescence, and then you've also got bubble collapse to kind of look at. So it's again, one more difference. Once you go down that path, you need freeze protection. Understand the differences that glycol also imparts. It's not just about freeze protection.
So how many things go in a glycol when you mix it? I mean, it's not just one or two chemicals. I mean, there's quite a list of things that have to go in there to do all these things: the anti-foaming, the pH buffer, the passivate, the metal, obviously the base glycol. I mean, like a dozen. I mean, what goes in there?
You know, it just depends on the formulation with respect to the application that you're trying to serve. But yeah, you're going to see, at least 3, and then no more than a dozen. Somewhere around 3 to 12, depending on what you're trying to do. That's typically what we see.
Yeah. And what I would add from a Caleffi standpoint here, that if you do want to get this air out, quickly or as quick as you can, this type of air separator, with the media in there, as opposed to just a scoop ramp or a little flow type of air vent, is going to certainly do a better job and a quicker job of getting those little bubbles out that go through there. So I think that's about it. I think we're down to about the last slide here. We got to keep rolling. Solar fluid, again, this is one of the products that we sell. It is a base product, a Dow base in there, but this is, we say 325. Is that realistic there, or is that just...
No, it's realistic in the sense that at that temperature and below, you should, if you do everything right, expect a useful fluid lifetime of 5 years or more. And that's really what that means. Obviously, if you're running the same fluid at 150 versus 325, you're going to get longer life than if you're running, right at the top at 325.
Yep.
You can think of it as that number as a tachometer. If you're redlining your car all the time, don't expect that engine to have the same number of effective hours as you would if you're running at more reasonable RPMs.
Yep. Well put. All right, typically when people are going to put glycol in a system, they're not going to hook it up to domestic water feed because you get the potential to dilute it. So I just put some ideas here. There's a lot of different products out there. You can see big commercial ones or little small residential that you basically put your fluid in there, and then it just maintains the pressure. And so if you're venting air out and you got to replace some fluid, this little device here is just going to pump it in. Then what are we showing over here?
Well, that's when we talked. Remember I said biodegradation?
Okay. Yeah.
That's fungi that feeds off glycol.
All right. Now, glycol always has to be sealed, too. You can't keep it in a container that isn't tightly sealed or open, because then this can happen in there, right, if you've got air.
Well, you can above the water line. So above the water line, those tank walls will be wet, and that's a ripe area for biogrowth. So, yeah, you have a very good point.
So if this isn't filled up and sealed, you can get the growth going in above whatever the level the fluid is in there.
Yep, and then it could wash off the walls if there's any kind of, turbulence.
So you could actually be growing and creating and putting a problem in your system if you're not. Number one, if this was sealed, that wouldn't be an issue. But I guess a couple of takeaways from that is keep this filled, number one, so you don't have that, space where something can grow in there. But also, it's got to be a tightly sealed unit, right? And this is a little system that Mark Etherington gave me this idea. This is one I made. If you've got to take glycol to boost up a system or fill a solar system that holds a little bit, you can pump it into a tank like this, pump some glycol in here and put a little pressure reducing valve and just take it out to the job so you don't have to carry a big pump in a cart. We've got, our fill valves can be used for that. Our new one, the 3/4 here, actually has a gauge and no check valve, so you just put it on there and pump it in and blow it back out into the system. We talked about temperature control. I think we've hit everything here. Any questions, Woody, before we get down to the last couple here? This was another one about compatible about all the components in there. I don't know.
Bob, I do have.
I do
have a number of questions. We have a number of questions, but I think that we may have to answer those offline.
Yeah, we're getting close to the end here. I would say most of the pump manufacturers in our industry for hydronics and stuff now have seals that are compatible with glycol. Most of the equipment that we use will say, glycol compatible. They actually give you a percentage typically, and so I don't know that you'd have to ask the pump manufacturer to give you a special type of seal or something like that. Is that your experience too, Kevin?
Most pump manufacturers will have a recommended seal for glycol, yes.
Recycling old fluid, what do you do when you take some out? You've got some fluid you want to replace. Some ideas here. I've been able to take small quantities, a couple 5-gallon buckets like to an auto repair shop or a Quick Lube or something. They obviously, when they drain your radiators, they put glycol in a drum and they recycle that. Somebody comes and picks that up and they buy it. A lot of your state or county website might have info where there's a recycler for that. Large quantities, we've used Safety Clean before when we were talking, hundreds of gallons like a school or a university project or something where that's got to be taken out and disposed of. You can hire them and they document it and make sure everything is done properly and legally, and then you've got that sheet to prove that you took care of it. It does break down quickly, right? I know in some of the glycols that they spray on airplanes for de-icers or that sometimes it just goes out in the pond and it breaks down quickly. In some airports it's flushed down the drain, right?
Very biodegradable, as we've mentioned, yes.
Yeah. It's just that you don't know what's in it as far as if it comes out of a heating system and some of the metals have broken down in there and you're flushing that down the drain. It's better to dispose of it properly. So.
Absolutely. And follow all your local and state regs. Yep,
as always. This is a great book. Is this available online, too? I don't know.
Yes, it is. It's www.dowfrost.com will get you there.
Yeah, this is a great thing. I don't know how often you guys update this, but I've got one from years ago, and I've got a more recent one. This is a great piece of literature that, again, it's not an ad. It's not a sales piece here. It just really explains the how and whys of glycol and stuff like that. It's got tables in the back that address the specific gravity, the density, all the different things that we've talked about. I would caution people, don't try and use an automotive, an RV antifreeze in your system. I know it's tempting because of the cost of it, but they don't have anything in there that's right for what we do. Anything on automotives quickly, Kevin, that's...
Well, they're exactly that, designed for protecting automotive cooling water systems. So they're going to have additives that are specific to aluminum at high temperature, and those additives are not going to have a long lifetime. A long life automotive antifreeze is about 5 years. And so you want to replace it every 5 years. Follow the manufacturer's recommendation. So, that's reason why you wouldn't put it in an HVAC system because you don't want to replace that fluid every 5 years. You want to have it run, hopefully, 20 years.
Yeah. And, this is, at the end of the day, what we're trying to avoid is that little smiley face on the left or coming home and seeing your Porsche under a foot of ice there. I don't know where this came from. I think... Greg Gibbs out of Shamrock Sales first gave it to me, but I don't know whose house this is or whatever, but that probably wasn't...
yeah, that's a great picture.
Is that something? All right, well, there we are, right on the money. I didn't leave much time for our poll, but we're still going to do our poll for that. But I want to thank Kevin for coming by today, and this was good information, and thanks for everything you did.
Well, my pleasure. I really enjoyed it.
And there's his contact information.